All right, so here we are. It is June 13th, 2016, and here we are again for the fifth class of this series. And we're now in Chapter 3 from the Wave Vector Mechanics book, looking at a few homework problems. Okay, so let's consider this system here. A 300 Newton force P is applied at point A of the bell crank shown. Compute the moment of the force P about point O by resolving it into horizontal and vertical components. So that's the first method. B, using the result of part A, determine the perpendicular distance from O to the line of action of P. All right, so let's do that thing. So let's just get this started. Now, so we're going to break this into components. Remember, in the previous class, we saw that there were two main methods for handling moments about a point. One, we could either break a force into horizontal and vertical components, which is very good for two-dimensional problems such as this, or we can handle it with a cross product. So in this one, we are going to use the method of breaking it down into horizontal and vertical components. So we have force P here, and it's going to generate a moment about point O. But of course, it's also going to generate a moment about any other point that we would consider. But we're looking at moments about point O. So how might we do this? Well, first what we need to do is I need to get the I need a couple things. I need the horizontal and vertical distance from point O to point A. Then I'm going to need also the horizontal and vertical components of the force P. So let me first get the components of force P. So Px is going to be equal to 300 sine of 30. 300 sine of 30 degrees. And we remember that this is a sine because here the angle is taken off the vertical instead of the horizontal. So that will come to, I'm just going to do this as decimals, 300 sine 30. And we'll come to exactly 150. 150 newtons. Py will be equal to 300 cosine 30 degrees, which is 300 cosine 30, which is exactly, or which is approximately 259.8. 259.8 newtons. Now, what I need to consider here is a triangle. So I need the triangle on here. I have a vertical and a horizontal component. Let me show you what's happening here. I have this Px, which has a magnitude of 150 newtons, and a Py, which has a magnitude of 259.8 newtons. 259.8 newtons. Now, this angle here is, of course, 40 degrees. And I need this length here and this length here. This is going to be, well, first the hypotenuse here. This is 200 millimeters. This is going to be 200 cosine 40. Which will be equal to 153.2 millimeters. And this will be 200 sine 40. I think I'm going to redraw the triangle after this, which will be equal to 128.6 millimeters. So I'm going to redraw the triangle just for clarity. Maybe a little bigger. Maybe not. So what I have here is I have 100, actually let me just convert this to meters, 0.1532 meters, and 0.1286 meters. And this is going to have, and then we have the two components of the force, 150 newtons and 259.8 newtons. 259.8 newtons. Now, I'm going to use the method of perpendicular distances here. So this vertical component is going to have a moment arm of 0.1532 meters. The horizontal component is going to have a moment arm of 0.1286 meters. Again, these are the perpendicular distances of the line of action of each of these. So this vertical component, if I look at its line of action along here, the distance between point O and the line of action is 0.1532 meters. The horizontal component, its line of action is here. And the perpendicular distance there is 0.1286 meters. So now I'm just going to do a sum of moments about point O. So I have a sum of moments about point O, counterclockwise positive. That's what this symbol means again, as a review from earlier. Now I will have to pay a little bit of attention to what is going to be positive and what's going to be negative. The about point O, this is clearly, the vertical component is clearly rotating in a counterclockwise direction. So it will produce a positive moment. The 150 Newton force, or 150 Newton component, is clearly rotating about point O in a clockwise direction. So it will produce a negative moment. So this is an example where the different components of the force actually generate different sign of moments. So the vertical component is going to generate a positive moment, while the horizontal component is actually going to generate a negative moment. Again, we cannot simply look at a force and say, oh, the force is positive, it has a positive moment, or the force is negative, it has a negative moment. We actually have to look at where it is in relation to the point we're taking moments about and sort of trace how it would rotate. If you imagine like an orbiting planet or something like that around a star. All right, so let's do this first. 259.8 newtons times a distance of 0.1532 meters minus 150 newtons times a distance of 0.1286 meters. Like that. So now we just apply multiplication, 0.1532. Okay, so I get 39 questions. I don't need to consider the sine and cosine because I already factored those in here. 39.80 Newton meters minus minus 19.28 Newton meters. And this comes to 20.52 Newton meters. Note, by convention, for units, we leave moment in Newton meters. If you remember from your physics course, you could probably recognize that, oh, that is the same dimensions as joules, and that is correct. But for the sake of moments, we leave it in Newton meters to indicate that it is a moment rather than, say, an energy measurement or something like that. Although, when you get to later courses, you will, when you start looking at deformations of materials, if you go down that route, if you're not studying electrical engineering or something, some sort of nonsense like that. Sorry. If you go into mechanics of material, if you take a mechanics of materials course, maybe even a structural analysis course, you will see that we actually do consider the deformation of materials using energy methods, but that's neither here nor there. So I now have the moment. This is the answer for part A. Now, all right, so what else can we do? Well, in part B, it's asking us for the perpendicular distance. Yes, the question was what is the point 1532? This is the length of this triangle here. It's the horizontal distance from point O to point A. See this triangle, 40 degrees here, and 40 cosine, 200 cos, see this entire thing from here to here, the hypotenuse is 200. The x component is going to be 200 cosine 40. Okay? Now, what's next? Okay, so for part B, I want to determine the perpendicular distance from point O to the line of action of P. What this is asking for is the distance from point O to the line of action of P. Now, we could use some fancy trigonometry and try to solve for that using trig methods, but actually there's a very simple way to do this. And this is to realize it doesn't matter what method we use to determine the moment. We could either use if we actually happen to know the exact perpendicular distance, we could just multiply by the magnitude of the force. But we already have the magnitude of the moment, and we have the magnitude of the force, so moment is always going to be equal to force times distance. It always is, where F is force, magnitude, and D is the perpendicular distance. This will always hold true. So what we can do is we can apply this relationship and say 20.52 Newton meters equals 300 newtons times D. Solve that for D. D is going to be simply this over 300. And this comes to 0.0684 meters or 68.4 millimeters. I'd be tempted to report this in millimeters because that's what we started out with.
That's the lever arm.
That is the, okay, so what is this again? This is the perpendicular distance from the line of action of this force to the point O. So it's this distance from here to here, basically. This basically is D. Questions on that? Okay. All right. Again,
So the distance is perpendicular, but not the force.
yes, in this case, the distance would be perpendicular. Well, actually, if we drug this force all the way back along here, at this point, if we move this force vector all the way back here, the force actually would be perpendicular, yes. Remember, we can move a force anywhere along its line of action and it won't change the result? Same thing here, yes.
So I want to know, like, in which case does the x component of the force is equal to the force times the sine?
Okay, the question was, in which case is the x component equal to the sine or the cosine? This is trig, this is previous course, Physics 1. Look at the trigonometry. Generally, but as a general rule, if the angle's taken off the horizontal, it's going to be cosine for the x component. If it's going to be off the vertical, it'll be this. If the angle is taken off the vertical, it will be the sine for the x component. But really, you just need to be able to apply the trigonometry that you already know. Okay, so moving on. Y'all got this? Okay, if not, the slides will be online. Okay. So, this looks very similar to the problem we worked through last time. Except this is the same problem we looked at last time, except set up a little bit differently. So we know that a force with a moment of 960 Newton meters about D is required to straighten the fence post CD. If the capacity of the winch puller is 2,400 newtons, determine the minimum value of distance D to create the specified moment about point D. This looks interesting. How might we solve this? There's different ways we could do this. Again, we could use the cross product. We could use perpendicular distances. We could use components. Tension times the distance? I don't think that quite makes sense. Because again, we can't just solve directly for the distance because this can, although actually, we have different ways we could do it. We could actually use a method of perpendicular distances. Let me think about that. That might be fun. I'm thinking. Maybe not, because we don't, oh. Negative by. Well, we know that already. It's 2,400 newtons.
But we can find the y component.
We could find the y component of it, but we need to solve for the thing. The real problem with this, the devil with this one, is that the x and y components of the force are going to vary depending on how big D is. So although we can solve for that without too much difficulty, in fact, let's do that. Okay, so I know that the okay, so let's consider this for a moment. I'm going to use component methods again, just for fun. So I'm going to have a Tx and a Ty again, as we usually have. I'm going to have D here. D here. Then we're going to have this triangle here. Actually, you know what? I think I'm going to draw this down here. Give myself a little more room. So I have this triangle to consider here. This is 0.2 meters. This is 0.875 meters. And then I need to find this hypotenuse. Do I need to find this hypotenuse? Actually, no, I don't think I need to find this hypotenuse. That won't be necessary. Okay. Now, I'm going to have a Tx and a Ty. I'll show my forces in red. Ty. And Tx here. Now, we need to consider how we get Ty and Tx. We have this triangle here to consider. Ty and Tx are going to be determined by this triangle here, essentially, from down to here, over to here, and over to here. So Ty and Tx will be proportional to the following triangle. We have along the hypotenuse, oh, actually first let me get the height and width first, 0.875 meters. On the leg here, I'm going to have D plus 0.2 meters. And then this is going to be the hypotenuse here. This is going to be, oh, this is going to be ugly very quickly, isn't it? Plus D plus 0.2 squared plus 0.875 squared, like so. D plus 0.2 here. Okay, D plus 0.2 squared plus 0.875 squared. So this is getting ugly very quickly, isn't it? We could do it this way, or we could also try to use trigonometry to solve directly for the perpendicular distance here. That might be another way to do it, if because that would be fairly easy to solve. Let me think about that, because then we would need to play with the trig a bit to see if we can. Okay, if we had, let me just think about this, because we can very easily get the perpendicular distance by realizing this. And then if we had that, we'll be able to easily solve for D? That's the question. Let me think about that. We'll know this. We'd have to think about the trig for a while, but it should be possible. Let me think about that. Meh. Okay, whatever. I'll just keep working with this one. Let me think. If we have this, well, we don't know the exact. I guess we're going to get really lost in the trig if we do that. I'm going to try to avoid doing that. Okay. So, but this is kind of a sticky problem.
We could solve for the angles and then use law of cosine to figure out the length of d.
Solve for the angles, then use law of cosines to figure out d. Let's see. How would that work?
So, what you would do first is, you know that the moment is 960.
Uh-huh.
And then you can figure out the length of CD.
Okay.
If you know the length of CD, then you know that the...
You cannot. So how are you going to get the length of CD?
No, the length from point C to point D, the length of that...
Oh,
that
okay. That, yeah,
hypotenuse.
that's not a hypotenuse, but yes, we could solve for the length of this, yes.
Yeah, so then once you solve for the length of that...
Uh-huh. Then we could easily find the perpendicular distance using this, and then we know that's a right angle, and we could solve for this angle. Actually, let me figure that back out. Like, okay, yeah, so we can easily get this fairly easily. This length, obviously, from D to C is fairly easy to get. We can get this based on perpendicular distances, and if we have this length and a right triangle and this height, well, let's see. Something law of sines. We can probably get this angle here. If we have this angle here, and we can probably get, well, can we get this angle here? That's the question. This is getting pretty ugly really quickly. That's the problem. It's just an ugly trig problem. That's the issue. I'm trying not to get lost in the trig. I think I'll just stick with this for now. Okay. So Tx is going to be equal to, that's going to be 2,400 newtons times d plus 0.2 over the square root of d plus 0.2 squared plus 0.875 squared, like so. And Ty is going to be equal to 2,400 newtons. And again, realize I'm not paying attention to the positives and negatives on this. I'm purposely leaving out the signs on these because we're going to take that into account in the moment calculation. 2,400 newtons times 0.875 over the root of d plus 0.2 squared plus 0.875 squared, like so. Now, I can say the sum of moments about d, counterclockwise positive, in this case is equal to 960 Newton meters, which is equal to, let's see, that is going to be equal to Tx. So Tx is going to generate a positive moment about point D. So this is 0.875 times Tx minus 0.2 times Ty. 0.2, oh, let me erase that. 0.2 times Ty. Times Ty. Like so. And the rest from here is just an algebra problem. Just a simple algebra problem, right? Couldn't be simpler. That's a really crappy joke. Yes? No, I don't believe so. That's something, I think you may be misreading that. There's something else is going on there. Okay. So let's see here. You know what? I'll try to actually go through this. Let me give myself a little bit more room to work through this. So I'm going to give myself another slide here. Call this slide 3.5. And, okay. So, let's see.
So something like this most likely won't be.
Probably not.
Copy the wrong picture because I mean they use the same pictures between different questions. So copy the wrong picture.
Okay, so first I'm going to realize that this, you can realize that there's going to be a 2400 in here and a 2400 in here. So first thing I'm going to do is to simplify the, actually, you know what, that's going to confuse people. Let me just write this here. So 960 equals 2400. I'm pulling out the 2400 in this. 2400 over root d plus 0.2 squared. So from each of these, I'm pulling out the root. Plus 0.875 squared. And then this is going to be times 0.875 times d plus 0.2 minus 0.2 times 0.875, I believe. Yes. Can you see how I got that? Just a little bit of factoring as I combine these together. That's all that is. Okay. So let's see. I'm going to bring this over here and the 960 as well. Or actually, 2400 over 960, 2.5. That'll look a little better. So I'm going to have square root of d plus 0.2 squared plus 0.875 squared equals 2.5. That's just 2.5 is just 2400 over 960 times this quotient here, times this parentheses here, times 0.875 times d plus 0.2 minus 0.2 times 0.875, like so. Okay, so this is quickly getting into an ugly quadratic territory, but that's okay. I'm feeling adventurous today. So I'm going to simplify everything in here, first of all. 0.875 times, well, first, let's just keep working on this. 2.5 times 0.875d plus times 0.2. I guess I could do that. Yeah, that would work. Yeah, let's pull out the 0.875. Different ways we could handle this. So this is 2.1875 times d plus 0.2 minus 0.2. Ah, look at that. That's interesting, actually. That's actually going to help us out quite a bit, isn't it? D plus 0.2 minus 0.2. So then these just go away. So I get 2.1875d equals our ugly root here. And assuming we haven't made a math error, which is a possibility.
Square both sides.
Yep, we'll square both sides. All right, so this is then going to be d plus 0.2 squared plus 0.875 squared, which is 0.7 0.75625 equals, okay, this squared, 4.7852 d squared. Okay, then this is going, there's a dot here, 0.7565. So now we have d squared plus 0.4d plus 0.0, let's see, 0.2 squared, 0.04, derp, plus 0.75625 equals 4.7852 d squared. Now I'm just going to bring everything to the right side and get, okay, minus 1, 3.7852 d squared plus 0.4 d plus this plus 0.04 plus 8 or 0.8. Oh, what just happened? Oh no. It's no worky. Oh man. That's not good. No, there is not an undo button, unfortunately. Uh-oh. Okay, well anyway, y'all get the idea, right? We have a quadratic, you solve the quadratic, you work through the math, hopefully it's not too bad. Okay. Nope, that doesn't. Lost a few notes there. Oh well, such is life. Already tried that, didn't work. Okay. There may be another method to do this. If we played with the trig, we might be able to figure that out as well. That's what I'm trying to figure out. You know what? Let me try that method as well. Maybe that'd be a little bit simpler. Let me try that in this slide, maybe. I'm going to try the perpendicular distance method. See, the first thing I can do is to realize that the perpendicular distance, d, is going to be m over f. This is d, what I'm calling d here. And d is going to be 2,400 newtons. Sorry, Newton meters. No, other way around, sorry. 960 Newton meters. 960 Newton meters over 2,400 newtons, which will be 0.4 meters exactly. 0.4 meters exactly. So now we get to play trig. Let's find, let me redraw this triangle. So maybe if we are really good at trig, oh, that's not going to work. Maybe, just maybe, if we're really good at trig, we can figure this out. Okay, I know this is a right angle, and I know this is a right angle. And let's see, I can find this angle, I can find this angle, and I should be able to find this angle here, shouldn't I? Okay. And if I know that, and then let's see. Yeah, if it's a right angle, we should be able to, actually we probably should be able to figure that out. Maybe that would be a little bit simpler method. Okay, I know this hypotenuse here is going to be the hypotenuse of this triangle, correct? So that's going to be 0.875 squared, the root of 0.875 squared plus 0.2 squared, right? 0.875 squared plus 0.2 squared, and that comes to 0.875 0.8978. So this is 0.8978. And this is the D we're looking for. Okay? And then, let's see. If I know that's the case, we know this is the D. And, yeah, I can find this angle here. Let me call this, I don't know, alpha, beta, and gamma, just for lack of a better label. So alpha, and we remember that this is 0.2 and this is 0.875, right? So alpha, for lack of a better name, is going to be the inverse tangent of 0.875 over 0.2, which equals 0.875 over 0.2, which is equal to 77 let's say 13 degrees. Now, I know this is 0.4, right? This is the perpendicular distance here is 0.4. And then beta, okay, so I know this is adjacent and hypotenuse, so it's going to be the inverse cosine, correct? The inverse cosine of 0.4 over this 0.8978. Which equals, so yeah, we're trying the angular method instead, over 0.8978, which is 63.54 degrees. Then gamma, if we look here, if this is gamma, beta, and alpha, these all three have to add up to 180 degrees because it's a full half circle. So gamma is going to be 180 degrees minus 77.13 degrees minus 63.54 degrees. 180 minus those two angles is 39.34 degrees. And now we simply say, oh, look. So we have this triangle here now. I'm looking at this right triangle here. I can simply say, yeah, the cosine of 39.34 degrees is adjacent over hypotenuse, so 0.4 over d. D is 0.4 over the cosine of 39.34 degrees. Man, that's supposed to be a C? Oh my god. And that comes to 4 divided by the cosine of 39.34. And I get 5.17 meters. This is probably the best way to do this problem, rather than messing with a really complicated quadratic formula and doing algebra for days. All right, questions on that?
Are you sure it's not 0.5?
No, that's right answer.
I got 5.17. Okay. All right. And unless I did a math error, but oh, actually, wait a minute. No, 0.4. Yeah, you're right. 0.517. Sorry, I forgot my decimal in my calculations. Point 517 meters. All right, questions on that? Feeling better now? It's just it's basically this is just we can do it different ways. We can do this as a problem of force components, or we can solve, and so we can do it two ways. One, a method of force components, then solving a really ugly algebra problem. Two, using method of perpendicular distances, and then just solving a really ugly trig problem.
See, like, I did what seems to be a completely wrong thing to do, but I got that answer. So I'm just like, I did 960 equals TYD. And I found the y component of the tension force, and then solved for d, and I got 0.5.
I don't know. I'd have to take a look at your calculations. something similar to that.
I feel like I'm completely neglecting X by doing that, but
Okay, so let's look at this.
maybe I'll talk to you later about it.
Yeah. Let's see. Completely neglecting X. Now you shouldn't be able to do that because that'd be a little bit strange. Okay. So here we have another system, problem 3.34 in the Beer Vector Mechanics book. Determine the value of A that minimizes the perpendicular distance from point C to a section of pipeline pipe that passes through points A and B. Okay, so let's look at this. That minimizes the perpendicular distance from point C to a section of pipe that passes through A and B. Let's see. So basically, the coordinates of point C are fixed aside from the z coordinate, right? That makes sense? The coordinates for point C are fixed aside from the z coordinate. So let me just start by writing this. I think the best way to start would be to start by just writing some coordinates out. So minimizes the perpendicular distance. Interesting. A, the coordinates of A, let me not use an equal sign. I'm just going to write some coordinates first. A has coordinates, let's see, I am going to use a proper cross product with this, I think. A is going to be, let's see, that's going to be in the x coordinate, it's going to be for part A. I don't. Where are you getting that 60? No, that doesn't make sense. No, the x coordinate, it's 0, I believe. Yeah, 0. 0 feet, comma, -8 feet. -8 feet, comma, 10 feet, right? B has coordinates, let's see, that is 24 feet, comma, 16 feet, comma, -18 feet. And those are the coordinates for point B. C is going to have coordinates, let's see, that's going to have coordinates, let's see, the x coordinate is fixed at -3 feet. The y coordinate is fixed at 2 feet. But the z coordinate is flexible and is basically at A. So that is the only coordinate here that can move about. Now, so we need to minimize the perpendicular distance here, right? We need to minimize the perpendicular, distance. I think I can apply principles of moments to this. So I'm going to try to solve this using principles of moments, which is why it's here. Imagine for a moment, imagine for a moment, imagine for a moment, I have a 1 kip force acting from point A to along line AB. Would you agree that if that force is fixed, the minimum moment will be the one where there's the minimum perpendicular distance? Does that make sense? So I can transform this, instead of a problem of asking to minimize perpendicular distance, I can transform this into minimizing moment. So we have this, I know how to do a moment calculation pretty well, so that's what I'm going to do. So I have this distance here, r. Minimizes from point C to a section of pipe that passes from A to B. Yeah. So basically, if I'm going to do the full moment calculation, just using these coordinates like we have before, and then I'll simply minimize it using a unit 1 kip load. So if we remember correctly, the moment about C is going to be equal to R cross F. So we'll need to get both, we will need to get vector R and vector F. Vector F will be, we can get entirely, vector R will need to be done in terms of A, coordinate A. So first thing I need is lambda BC. That is the unit vector along, oh not BC, sorry, AB. Lambda AB. Lambda AB. The unit vector along line AB. All right, so this is going to be, this means vector, of course, 24 feet, comma, 24 feet, comma, okay, that is negative 28 feet, right? Negative 28 feet. -24 feet, negative 28 feet, all over the square root of 24 squared plus 24 squared plus 28 squared. All right, and let's see what this comes to. 24. I'm just going to skip a few steps here to quickly calculate this. Square root of 24 squared plus 24 squared plus 28 squared. This over this. And I get, this is equal to 0.545, comma, 0.545, comma, negative 0.636, like so. And that is the unit vector along here. And the force vector then, because this force is just 1 Newton times lambda AB, Newton times lambda AB, our force vector then becomes 0.545 newtons, comma, 0.545 newtons, comma, negative 636 newtons, like so. And now our we will need vector R. I'm probably going to need to spill this onto a second page, so that's okay. So we're going to have R is the vector, not the unit vector, but the vector from C to A. So you know what, actually I'm just going to go ahead and call this CA, just to be very clear, this is from C to A. Notice again, we do not use a unit vector here, we use the actual vector. Because I'm not just concerned with the distance from here to here, I'm not just concerned with the direction, I'm concerned with the size of it as well. Because the longer the moment arm, the greater the moment.
How did you know to pick R in that direction?
That's just what we always do. The question is, how do we know to pick R in this direction? We always go from the point that we're taking moments about to the line of action of the force. That's the direction that the R vector always goes. So C to A, let's see. This is going to be 3 feet, comma, negative 10 feet, comma, A minus 10. Okay? A minus 10. Now I'm going to need to spill this over onto another page. Keep it. That's okay, we got space here. So this is 3 comma negative 10. Just need to write this down. A minus 10. Negative 10, A minus 10. So we have now, we have our RCA, which is 3 meters, or 3 feet, I keep putting meters, 3 feet, comma, negative 10 feet, comma, A minus 10. And we know that, oh, actually, this should be on the other slide. So we know RCA is equal to 3 feet, comma, negative 10 feet, comma, A minus 10. And I know the force vector is equal to 0.545 CA. So from C to A. Oh, actually, you know what? You're right. It should be 10 minus A. Thank you. 10 minus A. 10 minus A. And that's KIP. Oh, you know what? These should all be in KIPs. Sorry. KIP and KIP. So let me just get this proper. I know this is a bit messy. Sorry about that. Point 545 KIP, comma 0.545 KIP, comma A minus 10. And I was hoping this would turn out to be more of a parabola, but we'll see. It helps if we negative 0.636, yes. Negative 0.636 kips. Here. And so now we need to take the cross product. The moment is going to be equal to RCA cross F, which is going to be equal to then, it will be equal to, we're going to create a little table here, RCA and F. Let's see, I, J, and K. So we're going to have here point, or just actually 3, negative 10, and 10 minus A. And here we'll have 0.545, 0.545, and negative 0.636. Yes, I know. Negative 0.636. So after this, we just do the cross product. So this is going to be equal to, oh, let's see. Now, I only need to include, actually, okay, fine, that's fine. Let's just do the whole thing because I'm afraid that will just confuse people if I do that the other way. So I'm going to do negative 10 times negative 0.636 minus 0.545 times 10 minus A. Okay, and this is in the I, all this in the I. Then, let's see, in the I, then what's next? Then I can have, here, I want to say, for the J, I'm going to have minus 0.3 times 0.636, 0.3 times negative 0.636. Oh, sorry, 3, yes. Stray marks will do that. Three times negative 0.636 minus 0.545 times 10 minus a. All of this times j power. Then let's see. Now, do I even need to continue? So here's the thing. What I'm going to do is, in the end, I'm going to have a moment that's in terms of x, y, and z, the I, j, and k. And I'm going to basically, my final thing is going to be, I want to minimize the magnitude of this moment. So I'm going to do the square root of the x, the y, and the z terms of this, and then minimize it by minimizing a. Okay? So I actually don't need to worry about the z term. Yes, the z term will appear, but it's actually not going to matter here because the z term will not have any a in it. So we're not actually concerned with the final moment value. We're only concerned with the minimizing a, which is minimizing m. So plus something z. Oh, so something k. Plus something k. Again, it doesn't matter because all we're going to do is we're going to minimize that anyway. So this comes to, let's see, 6 minus 5.45 plus 0.545a. Plus 0.545a. Where did I get 6 from? Where did I get 6 from?
Well, from the 0.6, but where did you get the 0.6 from?
This 0.6, where did that come from? Oh, sorry, yes, 0.6, derp. Okay, yes. That was not written down correctly. Thank you. So that's 6.36 minus that. Plus 5.45 plus 0.545a. So this here and then this, all of this times I, which will actually equal 6.363 6 minus 5.45. So this will be 0.93 or 0.9136i. Then we do have to worry about the j. So this is minus 6 times negative 0.636 minus 0.545 times 10. Oh, it's a very similar thing here. Huh? Yeah, I'm not writing anything yet. Let me just show this in multiple steps, I guess. 0.6363 times 3 negative 1.909 minus 5.45 plus questions. Okay. Plus 0.545a in the j direction. Remember, I'm purposely ignoring the k. Please don't ask me where that went. As I mentioned, it's just something, it doesn't matter because we're just trying to minimize this. We're going to square all these anyway, so it doesn't matter whether this is a positive or negative. It's going to be squared, it's going to be a positive term. Okay, so this then comes to Oh, actually, something's not right here. I forgot my 0.545. Plus 0.545a squared. Or not squared. Erase like this. I. And then, let's see. So this is negative point that minus 5.45. So this is then, this ends up coming to plus, let's see, this will be negative and then a positive 7.359 minus 5.45a times j. Like this.
It's not. I think it's 0.545a, right?
Actually, yes, sorry, 0.545a. Keep missing the decimal places on these. 7.35 is basically 1.909 plus 5.45. Okay, so the final moment then, the actual magnitude of the moment. Again, we can consider moments as vectors in I, j, k components, or we can actually solve for their magnitudes just using a Pythagorean. The magnitude of m, and this is what we're actually going to end up minimizing. Again, we're purposely neglecting the k term because it doesn't have an a in it, so it's not going to contribute to the minimization or maximization. It's just like adding a constant, essentially. Is going to be, let's see, so we have 0.9136 plus, let me actually write this on the next line. Equals the square root of 0.9136 plus 0.545a squared plus, so this root's going to extend down over this whole thing, plus plus 7.359 minus 0.545 a quantity squared. So you have this big root, big ugly root here, and then you just minimize that, and you're done. Minimize it means to minimize this, you minimize it via any number of methods. You could set it equal to 0 and solve the quadratic. You could do whatever method if you're choosing. Once you have that, it's just math from there. All right, questions on that? We could set it equal to, actually, you know what, let's just, huh? Okay, the question is, why did we set it equal to 1 kip? Why did we apply a force of 1 kip? I am doing what I might call finding a unit moment. I am just saying, you know what? The distance will be minimized where this is not where it's 1 kip. It'll be the distance will be minimized wherever the moment will be minimized. And so for simplicity, I just gave it a moment. I gave it a force value of 1 for simplicity. You can pick any number of your choosing. It'll turn out exactly the same in terms of minimizing a. And in fact, we could probably solve for a. You know what? Let me just get this as if I set this equal to 0. Let me do a little simplified of the math here. 9 point. I'm just going to expand this out really quick. Plus 0.545x squared plus 7.359 minus 0.545x quantity squared. Basically, you end up solving the quadratic point. Oh, maybe not quite. Something. Let me think on this point. Oh, that'll work, actually. You end up, the root goes away, and you end up solving the quadratic 0.59405 a squared minus 7.025 a plus 54.99. And I remember, do you remember the formula, or do you remember the formula for the x-coordinate of the vertex of a parabola? The x-coordinate of the vertex of a parabola. I will see that this parabola clearly will have a minimum. It is definitely concave up because it has the positive coefficient on the squared term. So this will have a minimum. And the formula is actually negative b over 2a, where this is the b and this is the a. So it's actually going to be negative 7.025 over 2 times 0.59405 negative b. Oh, I got to give this negative here. And this comes to 7.025 over 2 times 0.5, basically 2 times this. And I get 5.91 feet. Huh? That it? Good. Close enough. This apparently the solutions manual said 5.92, but whatever. Close enough. Close enough for government work. All right. Simple, right? Easy. What could be simpler? All you got to do is remember your formula for the vertex of a parabola, or alternately, you could just use a simple derivative and get set it equal to 0 for the minimization. Negative b over 2a for the vertex of a parabola, but that's just the first derivative of the y equals ax squared plus bx plus c. Y prime is ax plus b, set this equal to 0, x equals negative b over, sorry, I can't math, 2ax. So x is b over negative 2a. That's where that comes from. It's just a very, very simple application of first order derivatives. All right, questions on that? So, just going through a few simple problems, right?
Just don't put that one on the test.
Just don't put that one on the test. Okay, I'll try not to do that.
Waste an hour and a half.
All right, so other questions. I think we've gone over enough homework problems, but
Break time?
let's see, break time. Let me think about that. Should we do break time? Sure, why not? Let's take a quick break. The material I have on here for today is a little bit less than what we've went on some other days. So that's okay. Let's take a quick break. We'll come back and look at some new theory and do an example problem or two.